Okay. So first we will study the three modes of heat transfer. The three modes of heat transfer are conduction, convection and radiation. What is the conduction? Conduction is the heat transfer in a stationary medium. If the medium is stationary and there is heat transfer through a medium, then you say that heat transfer is by conduction. So this is the heat transfer in a stationary medium. When there is conduction, there is no movement. Okay. For example, if there is heat conducted through a fluid or a liquid, then if the liquid is not moving and then heat is getting transferred to the liquid, then the mode of heat transfer is called conduction. Convection is the heat transfer due to fluid flow. If there is a fluid flow or fluid motion and there is heat getting transferred because of the fluid flow, then you call that heat transfer mode as convection. Finally, radiation. All bodies or all objects, all surfaces above absolute zero temperature, that is absolute 0 Kelvin, emit thermal radiation. So thermal radiation is a mode of heat transfer that is taking place all the time. My body surface is above 0 Kelvin, so it is also emitting radiation. The board is above 0 Kelvin, that is also emitting radiation. The sun is definitely at a very high temperature, that's also emitting radiation. But the amount of radiation depends on the temperature of the surface. So if the temperature of the surface is very high, then the amount of radiation is going to be very high. If the temperature is low, then the radiation emitted is low. For example, the radiation emitted by the sun is very high because the sun's temperature is high. The radiation emitted by my body or the radiation emitted by the board is lesser because the surface temperature is going to be lesser. So these are the three modes of heat transfer very quickly. Now we learn three rate equations for the three modes of heat transfer. For the first mode, that is for conduction, the rate equation is called the Fourier's law. The rate equation is called the Fourier's law of conduction. What does the Fourier's law say? The heat transfer is given by minus Ka dt by dx. Or the heat transfer in the x direction, if I call it as Qx, Qx is given by minus Ka dt by dx. What the law says is the heat transfer is directly proportional to the area. The heat transfer is directly proportional to the temperature gradient. That is, Q is directly proportional to A and Q is directly proportional to dt by dx, the temperature gradient. So you can see Q is directly proportional to A dt by dx. This is the heat transfer in the x direction. Now if you want to remove the constant of proportionality, you put an equal to and there is, or if you want to remove the proportionality symbol, you put an equality symbol and there is a constant of proportionality. This constant of proportionality, this is called the thermal conductivity. The K is the thermal conductivity. That's the property of a material. It's the material property. The Fourier's law was, it's a phenomenological law, meaning it cannot be derived from first principles. Based on observations, based on the observations from various experiments conducted by Fourier, he concluded from the Fourier law. He concluded that Q has to be proportional to area and Q is proportional to the temperature gradient, and hence Q has to be equal to minus Ka dt by dx. This constant depends on the material and this is called the thermal conductivity. What are the units in this formula? It's a very important relation. Fourier's law is very important. What are the units in Fourier's law? K is thermal conductivity. We'll decide the unit of K finally. First, Qx is the heat transfer rate in watt. Always the capital letter Q will denote the heat transfer rate in watt. X denotes the direction. It is the heat transfer in the x direction. Now A is the area is the area perpendicular to the x direction. Now you know the SI unit of area is meter square. And dt by dx is the temperature gradient. It's the temperature gradient. What is the unit of temperature gradient? dt will be in Kelvin or degree Celsius. dx will be in meter. So this will be either Kelvin per meter or degree Celsius per meter. Because dt is in degree Celsius, that's a change in temperature. This is a change in distance. So the temperature will change over a particular distance. It will be in either Kelvin per meter or degree Celsius per meter. Now what is the unit of K? To rearrange, K is minus Q by A dt by dx. Right? So the unit of K has to be watt per meter square, and this is in degree Celsius per meter or Kelvin per meter. So this meter and meter square cancels. You get watt per, let me call it as Kelvin, watt per meter. So the unit of K, the thermal conductivity, is watt per meter Kelvin. That's the first law that you have to study. That is the law governing the heat transfer called conduction, which is the Fourier's law. In the Fourier's law, you have to remember the various quantities along with their units, and the important parameter that comes, the material property that is very important, is called the thermal conductivity. Okay, the second law is called, this is for convection, and this is called Newton's law of cooling. The rate equation for convection or convective heat transfer is called Newton's law of cooling. I illustrate Newton's law of cooling. Suppose you have an object at a very high temperature. Say the surface temperature is very high, say 100 degrees Celsius, and then you have a fluid that is flowing over the surface. There's a fluid flow over the surface, and the temperature of the fluid, let me call it as T infinity. So T infinity is the temperature of the fluid, and Ts is the temperature of the surface. What will happen? Say, suppose this is at 100 degrees Celsius, and say the fluid is at atmospheric temperature. You have a very hot surface, and you have cold air blowing across the hot surface. What will happen between them? Heat transfer will happen. Heat will transfer from the hot surface into the cold air, because of the temperature difference, there is going to be a heat transfer. Now, what is going to be the heat transfer rate? It is given by HA, T minus T. Okay. So A is the area exposed to convection. H is called the convective heat transfer coefficient. Ts is the surface temperature. T infinity is the fluid temperature. Essentially, what does it say? The heat transfer is proportional to the area. If the area is high, then there will be high amount of heat transfer. Second, the heat transfer is proportional to the temperature difference. If this temperature difference is very high, then the heat transfer will be very high. So Q is proportional to A, Q is proportional to Ts minus T infinity. So Q is proportional to A into Ts minus T infinity. If I want to remove this proportionality symbol, I have to put an equality, and then I have the constant of proportionality. This constant of proportionality is called the convective heat transfer coefficient. So again, let us write the units along with the quantities along with the units. Q is the heat transfer rate. Now this heat transfer is due to convection because it is due to fluid flow. Now the heat transfer rate is always in watt. Capital Q is always in watt. A is the area exposed to convection. So whatever is the area or along which convection is taking place, that area is A. Ts minus T infinity. This is the temperature difference that drives convection. Whatever is the temperature difference due to which convective heat transfer is taking place, that is the temperature difference Ts minus T infinity. This is the temperature difference. This is in either degree Celsius or Kelvin. Now let's decide the unit of H. What should be the unit of H? the equation for H. H is equal to Q by A into Ts minus dT. Right? Now Q is measured in watt. So the unit of H will be watt. A is in meter square. Ts minus dT, the temperature difference, is in Kelvin or degrees Celsius. So we call it as watt per meter square Kelvin. So thermal conductivity was measured in watt per meter Kelvin, whereas the convective heat transfer coefficient is measured in watt per meter square per Kelvin. So H is called, if we write H is called the convective heat transfer coefficient. The convective heat transfer coefficient is a complicated function of the fluid velocity, the fluid properties, and a lot of parameters. This is the hardest to find in any convection problem. Essentially, in the second unit, where you will study convective heat transfer, the main idea is to estimate the convective heat transfer coefficient. It's a very difficult parameter to estimate. We have a lot of correlation from experimental data, a lot of theory, so gives you some equations for convective heat transfer coefficient. But this will be the main focus of any heat transfer by convection. In any convection problem, you want to know what is going to be the convective heat transfer coefficient. Once you know convective heat transfer coefficient, you can easily find the heat transfer rate by multiplying this with the area and the temperature difference. So again, to summarize, the Newton's law of cooling is the rate equation for the second mode of heat transfer, which is called convection. It says that the heat transfer rate is directly proportional to the area and directly proportional to the temperature difference, and H is going to be called as the convective heat transfer coefficient. Now coming to the third rate equation, this is going to be the important equation for thermal radiation, and definitely you would have studied this in your school physics, which is called the Stefan-Boltzmann law. Definitely you would have studied in your school physics this law, which is called the Stefan-Boltzmann law. That's going to be the rate equation for radiation. What does the law say? It says the emissive power of a black surface is directly proportional to the fourth power of its temperature. If you have a black surface or a black body, which is a very good emitter of radiation, the emissive power, that is the heat per unit area emitted from a black surface, is proportional to the temperature of the surface, not the temperature, the fourth power of temperature. So if T is very high, then T power 4 is going to be extremely high, which means there is going to be a lot of radiation. If T is low, then T power 4 is very low, which means there is going to be very little radiation. For example, for my surface, the radiation is going to be less. The radiation from the sun's surface is going to be very high because the radiation is proportional to T power 4. And as usual, you have a proportionality constant here, which you call it as sigma, and sigma is called the Stefan-Boltzmann constant. EB is the emissive power of a black surface, and I'll come to that when we talk about radiation. The emissive power is the heat flux, the heat transfer per unit area, and T is the temperature. Here in radiation, because you have temperature power 4, it is always the absolute temperature. You cannot use degree Celsius temperature here. Whenever you do radiation problem, you have T power 4. You always substitute the absolute temperature, that is temperature in Kelvin. So T is the absolute temperature. It is always in Kelvin. And sigma is called the Boltzmann constant, the Stefan-Boltzmann constant. And this constant has a value 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. Okay, you know this is in watt per meter square, that is Kelvin power 4. So the unit is watt per meter square Kelvin power 4. This value is very easy to remember. It goes like 5678, 5.67 into 10 power minus watt per meter square Kelvin. So this will be the rate equation that is governing radiation, which is the Stefan-Boltzmann law. So first you have to understand the three modes of heat transfer and three rate equations for the modes of heat transfer.